Let's do it. Okay, this question is written for ionization energy. We haven't quite got to that yet. That'll be our next section, but we can do this for radii. What you need to know is that the radii increases in size as it goes from to the left and down on the periodic table. We have no trend for the left and up. From left and down, it gets larger. So all you need to do is just rank them accordingly, and you'll be set. So that would be, fluorine would have to be the smallest. It's the most up and to the right. Then it looks like nitrogen comes next. And let's see, it looks like aluminum comes next. And then go a little more to the left, there's magnesium. And then down and to the left, there's potassium. And that would be it. Let's say, for example, we tossed in an anion or a cation into this mix. So let's say we put in aluminum 3+ in this mix of elements. Cations are significantly smaller than their neutral counterparts. So much so, if I see a cation, I'm automatically putting it as the smallest. Okay? If I saw an anion, the opposite would be true. So if I saw an anion like this, anions are significantly larger than their neutral counterparts. So because of that, I would automatically put an anion at the biggest side, the largest side. Okay? That's it. Just follow the trend to the left and down. It gets larger, and that's what you need to know for radii. Why does this happen? Because of screening. And we also should talk about Z effect within that mix. Okay, that's it with that problem. The next section will be ionization energy. So you see how to do that in just a moment. And here we are. So check, you did that last time. And today, check. We're going to start chapter 9. It's exam 2 Eve. That means all new material that you hear today will be on the final. Okay? It won't be on exam 2 if it's new material. And I'll talk a little bit about the exam at the end of the class today. I have office hours as normal on Wednesdays. Okay. Was there any questions from last time that I can answer right now before moving on? Remember, all stuff up to 8.3, including section 8.3, is going to be on exam 2. No, that's totally fine. Hopefully, for the most part, maybe except for section 3 of this chapter should feel like the easiest one you've had in a while. It's going to go so fast that we're actually going to finish today, this section as well today. And this, right now we're going to go into I, which in this chapter is ionization energy. You probably heard me use this term a little bit from time to time. This means that, let's say you have something neutral like magnesium, you can make magnesium plus electron, basically removing an electron to make an ion. That requires an ionization energy. We'll call this I1 because you can do this more than once. You can take Mg plus and go to Mg2 plus an electron, and that would be I2. So in order, in this case, to form Mg2 plus, you would sum ionization energy 1 and ionization energy 2. So there's very little math in this chapter. You'll see a little bit in the homework, especially using the table on page 325 of the textbook. I think there's one question with silicon that uses that table. In that case, the two math problems you could possibly do, one is just saying, they would ask you, how much energy would it take to make the Mg2 plus? And you'd have these two, and you would just add these two numbers. That's one type of math problem. The second type of math problem you could be asked with ionization energy would be involving this old formula from the last chapter, the Ritter Equation. Okay, if something is ionized, that means the electron is removed. What would be N final? N final, the final orbit, should be a really big number because you're going out infinitely outside of the atom. And so what we would say is N final goes to infinity. What does that mean? 1 over infinity squared is 0. So the change in energy, it's basically the same equation, just the N final goes to infinity. It's just N initial squared. Now there's one more piece of information I kind of alluded to in the last chapter, but I didn't say much about it. In this, there's also one more term that goes on here, and it's a z squared that you'll see, you should see in the chapter, or a z effective squared. What's capital Z mean? That's atomic number. So for example, hydrogen's 1, helium's 2, lithium's 3, beryllium's 4, etc. So the previous chapter, chapter 7, we were only working with hydrogen, if you didn't realize that. It was only hydrogen. And so in that case, hydrogen has an atomic number of 1, and 1 squared is just 1. So I didn't write that part in the equation, and you wouldn't have seen it when we were even in the chapter, probably. But now we have to add it, because in this chapter, sometimes they'll ask you about, say, lithium. And so for lithium, you'd have to put a 3 squared as this term, because you'd have to add in the atomic number. Okay? So just know that that term is there. We didn't use it again in the last chapter because we were talking about hydrogen, and Z is 1 for hydrogen. Okay, so this is a second way to calculate ionization energy if you are asked for it. Okay, what's the trend for ionization energy? It's the opposite of radius. So basically, if you can imagine, if the radius is really big, and so there's a really big, huge atom, it's easier to remove an outermost electron. And the reason it's easy to remove it, thus a low ionization energy, it's easy to remove it because it doesn't have a strong pull towards the protons in the nucleus. Protons in the nucleus is what's keeping it on the inside. If it's so far away it's not really attached to it, it's easy to remove. So as radius goes up, ionization energy is going to go down. And I'll write that down for you. As radius goes up, ionization energy, I, will go down. And that's again because it's further from the nucleus, it's less attached. So if we were going to do this problem from before, here, you would just flip the order of all these. If you're going to do this problem for ionization energy, you just flip the order. So fluorine would have the largest ionization energy because it's the smallest. Potassium would have the smallest ionization energy. So that's it. Okay? So the trend is opposite that of the radius. It follows, just like the other properties that were mentioned, periodic law. Periodic law, again, if you don't remember, if you arrange something according to the atomic number, you should see some periodicity or some repeating patterns. And you can see it looks kind of ugly, but it's going up and down. And that's periodic law. If you arrange it according to atomic number, you should see some patterns. Okay, some up and down nature. Okay, and so basically there's a lot of possible properties that could follow periodic law. The chapter just highlights a few of them. So radius was the first one that has a periodic trend. This is the second one that the chapter highlights. Really, well, I'll mention all of them later. Another one that the chapter mentions is the next section. So that's all you need to know for ionization energy. Let's go on to the next section. That's section 5. And in the reader, we're on page 80. In the textbook, we're now on page 327. section 5, I believe. Yeah, 5. EA, or what's called electron affinity. EA, or electron affinity. Electron affinity is kind of the opposite of ionization energy. So let's say we had a bromine, and you add an electron. Instead of removing, you're adding an electron to make Br minus, which nonmetals like to have the anions to complete their noble gas configurations, and metals like to be cations to complete their noble gas configurations. So this would be primarily for nonmetals. This would have some electron affinity energy. Okay. Now, if in your notes you mark this, I'll get a different color. This number is typically negative, less than 0. This number way up here, ionization energy, these are greater than 0. Okay, so you want to note that. The negative or the positive just shows direction of flow. Okay, so in receiving the electron, energy is given off. Or the reverse is true. For ionization energy, you put energy in, and the electron comes out and is ionized. So the negative just shows the direction of flow. Negative means leaving the atom. For positive, for ionization energy, that means it's going into the atom. Yeah. Okay. This is similarly follows actually ionization energy. So the trend follows ionization energy. It increases. It basically follows the radius. It's opposite of the radius. So the bigger something is, the easier it is to remove or add an electron. Because it's so big, if the electron's on the outermost shell, it's not affected by the nucleus as much. So since it's so far away, it's easier either to remove or add one. However, in contrast to ionization energy, where electron affinity increases as you go to the right and up, but increases negatively. So this increases negatively, where ionization energy increases positively. Okay? It doesn't have this one doesn't have a really nice trend, but it does have a general trend following, again, the ionization energy, which is opposite the radius. Okay, let's do one more, and I'm going to put it in this section here. And we're going to see it again in the next chapter, and that's called EN, and that's electronegativity. This chapter in the textbook doesn't really cover it. At this point, it covers it later, but I think it makes more logical sense to at least mention it at this point. Electronegativity. Electronegativity is, what does this symbol mean? Is proportional to, electronegativity is proportional to, and this is a combo of ionization energy and electron affinity, so that's why it's nice to mention here. Okay, it's proportional to both those terms. The ionization energy and the electron affinity. Remember, electron affinity is negative, so by subtracting it, you're actually adding it. Okay, so what does this mean? Electronegativity, where ionization energy is the energy to remove an electron. Electron affinity is the energy to add an electron. This is kind of the ability to hold electrons, if you will. So it's the ability to, and I'll write this down, not lose an electron and in combination to gain one. So there's a push-pull factor, if you want. Electronegativity is the ability, first, how well can it not lose one? And secondly, how well can it gain one? So it's a combination of the other two factors. Okay? Ionization energy, as it gets larger, you will not lose electrons. As electron affinity gets larger, you're going to gain electrons. So it's a combo effect. And as you'll see in the next chapter, this will vary. We're going to talk about this one a little more than the other factors. This will vary from 0 to 4. Okay, it goes from 0 to 4. It's a continuum. Okay? And I'll elaborate this a little bit more, you'll understand what this means. But if you find the electronegativity is somewhere between 0 and 1, we typically call this a covalent bond. And you'll see more about that in the next chapter. And if it's somewhere between 2 and 4, we typically call this an ionic bond. And there's a nebulous region in the middle between 1 and 2. Okay? So, again, you'll see the words covalent and ionic more in the next chapter. So that brings us to the following table. And I'm just going to show you the one in the reader on page 80. There's something similar in the textbook. Essentially, this table right here is a summary of the whole chapter. Outside of just the whole idea of periodic law, you need to know the trends, and that's what this chapter is about. How does something trend on the periodic table, at least? And so radius, screening, or shielding, those are the same things. And metallic character increases go to the left and down on the periodic table. And then electron affinity, ionization energy, and negative electron affinity increases go to the right and up. Z effective only increases as you go to the right. Up and down the periodic table is a little more complicated. It involves something called Slater rules, which is beyond our scope. But what I would do if I was taking the final, and this is going to be most helpful on the final, when I walk into the final, as soon as I'm able to open it, I would go to the back page and write this stuff down so I didn't forget it. Okay? And just write it right on your periodic table. What you'll need for exam 2 is only the radius. Radius, shielding, screening, Z effective trends. Okay? So if you want to do that on exam 2, it couldn't hurt you long. All right. There are a couple more tidbits of the chapter. They're mostly terminology and some simple concepts, so let's hit those. And first, next we'll go on to section 6. Section 6, magnetic properties. This is in the reader on page 81 and the textbook on, let's see, page 328. Okay, this is one of those things we're going to introduce now. We're really not going to use it too much until chapter 10. But we'll introduce it at least. There's a lot of different types of magnetism. So there's anti-ferromagnetism, there's ferrimagnetic, there's ferromagnetic, which is probably the one you're most used to. You can have a permanent magnetic field. But we're going to talk about two specific types here. One is called diamagnetic, and these will be most pertinent to us, diamagnetic and paramagnetic. Diamagnetic. Dia means what? Two. Okay, sometimes people think para means two because they want to spell it like this. Para. Okay, that's not para. Okay? Dia is the one that means two. And so dia means all electrons are paired. So there's an up spin and a down spin. If all electrons are paired, diamagnetic, then it'll be diamagnetic and experiences zero or hardly any magnetic field. So there's almost no magnetism with diamagnetic. There's a little bit. Paramagnetic means there's at least one unpaired electron. At least one unpaired electron. If there's at least one, then we call it paramagnetic, and those unpaired electrons will cause a magnetic field. So paramagnetic will be magnetic as we think about it. Okay? So the one on the right is magnetic, the one on the left is, for the most part, not. But if you look online, and some people do, so I'll just tell you before you look, there's this weird association with diamagnetism, scientists, and frogs. And what some really weird scientists like to do, and you can look online, you'll see this exact picture. They like to kind of magnetize frogs. I don't know why frogs would do it. And put a little diamagnetic field in there. And so they can actually levitate frogs. This is a levitating frog via diamagnetism. Okay, so there is a slight magnetic field with diamagnetism, but effectively it's pretty minimal. So we consider it, for our class, non-existent, but it is possible to do some things in the diamagnetic field. Okay, how can we use this concept to do any problems? Well, mostly, again, we're going to use it in the next chapter. But let me give you an example. Let's look at moly, which is molybdenum number 42. Let's write it. I want to know if this is para or diamagnetic. Is this para or diamagnetic? Well, what would you do? You write out the electron configuration. Make sure you can do this for sure on the exam 2. Notice I wrote it like this because why is it not 4s2? Yeah, this is one of those exceptions, one of the 2 exceptions for transition metals. Anything in the 4th or the 9th column of the transition metals will only half fill the s's, and that reduces pairing. And so if you write this out more like this, in this kind of orbital format, 5s, and you draw the boxes out, like that, for D, and let's get a different color pen, fill in the electrons. It's 5s1 and 4d5, 1, 2, 3, 4, 5. In this case, what is it, para or dia? Paramagnetic. It'll exhibit a magnetic field. It's magnetic, and in this case there's 6 unpaired electrons. We only needed 1, but there happens to be 6, which is fine. And so it's definitely magnetic, it's definitely paramagnetic. Let's do one more. This is another good example because it illustrates the other exception. We're going to do zinc 2+. If you don't know how to do these right off, what I would do is do the neutral zinc first. The neutral zinc would be argon. And you might, yeah, let's just do this. It's 4s2 3d10. Well, with zinc 2+, it's going to lose 2 electrons, and this is the second exception, just to remind you of how Chapter 7 went for electron configurations. The second exception for transition metals, and really anything under the staircase, the first electrons it loses are the s electrons, not the d's. So because I'm losing 2 electrons, I'm going to lose those 2 right there. And this will be argon 3d10. Not 4s2 3d8. And so, if we draw this one out, there, argon, here's a 4s, and then the 3d. Here's the 3d, and let's fill in those electrons. The 4s has 0 electrons, the 3d has 1, 2, 3, 4, 5, and then I start pairing, 6, 7, 8, 9, 10. So what would we call the second one? We would call it diamagnetic. So where the first one was, zoom out a little bit, paramagnetic. This one will be diamagnetic. Diamagnetic, because everything is paired, it will essentially exhibit no magnetic field. Okay? So these are pretty typical problems that you would see on a final, where we give you something and we ask you, is this para or diamagnetic? You have to write out the electron configuration and see if you find any unpaired electrons. Okay. Any questions? Are you ready to move on? There's a question? Yes? Move on. That's right. Yeah. For paramagnetic, let me repeat her question and I'll illustrate that for you as well. For paramagnetic, you only need 1 unpaired electron. So for example, let's say I changed the problem and I made it like this. Let's say that was paired. I had one here, 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 and here. That would still be paramagnetic because there's 1 unpaired electron. Okay? So just need 1. Yes, depending on, in general, yes. Yeah, it would be S1 4D10. Either way, it would be paramagnetic. Okay, let's go to the next section. These sections all go fast. This is section 7, and I kind of, in the reader, I just call it other stuff, other things we haven't covered yet. This is page 81, or in the textbook, let's see what the textbook calls it, periodic properties of the elements, which is what the whole chapter is about, so I don't know why the section is called that. But anyways, it's other stuff they haven't got to yet, kind of a buffet of extra topics. Okay. This would be on the exam, at least the terms reducing and oxidizing agent. Okay. Which one is most likely to be a metal? This is going to be my question. And which one's most likely to be a non-metal? The oxidizing or reducing agent. So let's think about it. Reducing agent, for reducing the top one, am I increasing oxidation state or decreasing it? For this one, you need to think, reducing agent, that means oxidation. Oxidizing agent means reduction. Okay? So a reducing agent is oxidized. That means the oxidation state is going up. Here, the oxidation state is going down. Okay? Now, which one, top or bottom, is gaining electrons? If I'm going up in oxidation state, I'm losing electrons here, and I'm gaining them here. Okay? So let's say it again. Reducing agent means oxidation. That means I'm increasing the oxidation state or losing electrons. Oxidizing agent is reduction. That means I'm decreasing or reducing my oxidation state. That means I'm gaining electrons. Okay. Does a metal want to gain or lose electrons? Lose, yeah. So, thus, therefore, this is most likely a metal, and this one is most likely a non-metal. So, reducing agents are typically metals, or metals are typically oxidized. Non-metals are typically oxidizing agents or reduced. Okay, let's do a little more. Let's go to the next slide here. All right. Let's take calcium oxide here. I'm going to add water to it. Okay? And I'm going to form calcium hydroxide. Okay? Is this an acid or a base? This is a base, one of your strong bases. So we call this a basic oxide. And in general, metal oxides are basic oxides. They're basic oxides because in water they form a base. Okay, metal oxides are basic oxides. Okay, let's look at another one. Anybody know what this will form? This is a reaction from chapter 5. I heard somebody say it, carbonic acid. And basically, if you're doing the net ionic equation, you form carbonic acid, you should automatically write these two. But there is a reverse equilibrium where it goes towards the carbonic acid. And in this case, obviously it's acid if it's called carbonic acid, so we call this an acidic oxide. Thus, nonmetals like carbon is a nonmetal. Nonmetals form acidic oxides. Basic oxides, in our example, calcium, are metal oxides. Okay, so metal oxides, we call basic oxides because they form bases. Non-metal oxides are acidic oxides, and we call them that because they form acids. Okay. By the way, this is why our coral reefs are having so much trouble. There's so much CO2 in the air because of emissions. When it gets absorbed into the water, it forms carbonic acid that acidifies the ocean water and starts to tear apart the coral reefs, like the Great Barrier Reef and such things. And that's why the reefs are having so much issue because of our CO2 emissions. We have too much acidic oxide in the air. Okay, and one more thing in this other section is basically the last possible, one of, I guess, 3 possible math problems you can have. So again, there was the 2 math problems I showed you could possibly have from this chapter were in the ionization energy section, where you either need to know how to add given ionization energies or be able to calculate it using grid work. This would be the last possible type of math problem you can have. This also involves kind of adding, so it's not too bad. Let me show you how this works. In this example, I know that the atomic radius of rubidium, Rb, is 2.48 angstroms. Did I already define angstroms earlier? If I haven't, 10 to the 10 angstroms, it's an A with a 0 on top, is 1 meter. That would be a conversion given on the exam. Angstroms is a pretty common, non-SI unit, but a common unit because it forces the radius to be a counting number, like 1 or 2 or 3. Like in this case, 2.5 is the radius. It says cesium has an atomic radius of 2.66 angstroms. What's the atomic radius of francium? Okay, and notice I put it in the order of the periodic table, rubidium, cesium, francium, in that order. And this is what Mendeleev and others used to predict properties of elements that were unknown. So you can use this concept if you want to predict some of the radii of unknown elements, say of like whatever 120 would be. Okay? Just following the same kind of procedure. It's an estimate, but it turns out to be pretty interesting. So for example, here's how you do it. If this follows periodic law, which radius does, then the difference between these two is how many angstroms? Okay, well get out your calculator if you're not sure. It should be that. Okay, so that means the difference between these two should be 0.18 angstroms because it follows a somewhat repeatable trend. In that case, I'm just going to add 0.18 to 2.66, and that's going to be 2.84 angstroms, and that's the radius of francium as an estimate. And so just through some simple addition and subtraction, you can estimate the properties of unknown elements. And this follows periodic law. If you want to see more on this, there's something called that I have called periodic law calculations. I'll do some other examples. Okay. Any questions on any of that stuff?